Hello, everyone. I'm Billy Younger, and welcome to Special Relativity 002. In Special Relativity 001, I introduced the two principles of special relativity, the one about the laws of physics being the same in all inertial reference frames, and then the other one, the constancy of the speed of light. And I then used that to compute the time dilation formula. I introduced a concept called of gamma, which is the gamma factor in relativity, and another quantity called beta. For a refresher, let me show you on my document cams what those were. So we had actually introduced you to the idea that the amount of time a person sees go by for a person riding in some vehicle moving at a velocity v greater than zero is the person riding along in that vehicle's time divided by 1 minus v over c quantity squared under the square root. This is called the proper time, and that's the time measured by the clock that was with the person at both the beginning and the end of the interval. This is a time measured by someone who sees that clock moving or that person moving with some velocity v. I made this a little shorter by calling it gamma times the proper time, where gamma is defined to be 1 over the square root of 1 minus v over c quantity squared. And that I made even shorter by calling it 1 over the square root of 1 minus beta squared, where beta was defined to be v over c. So these are a couple of abbreviations that might come in handy. And now that I have that and reminded you what that was, I'm going to now work a problem by first sharing the screen so you can see what the problem is and then solving it. So in this problem, I'm asking you to calculate the values of beta that make gamma equal to 2, equal to 3, equal to 4, equal to 5, and then 10, 100, 10,000, 1,000, so on and so forth. There's a bunch of different ones. I've left 1,000 off there. I don't know really why I did that, but I'll put it back in now. And basically from that, I'd like you to look for patterns and things like that, but it's also useful to have some idea what velocity something must have in order to have a relativistic factor of 2. So when you have a relativistic factor of 2, that literally means the proper time multiplied by 2 is the time that someone else would see if you happen to be traveling at that speed that makes a gamma equal to 2. Same thing with a 3, same thing with a 4, same thing with a 5. Now, I'm really going for that, and then I'm going for powers of 10, basically. So this is 10 to the first power, 10 to the second, 10 to the third, 10 to the fourth. This is 10 to the sixth, so on and so forth. But you can go through many of those. I'm going to solve it algebraically and then use that general expression to work out all the individual answers. So let me stop sharing screen, turn it back to my document cam. And when I say that gamma is equal to 1 over the square root of 1 minus beta squared, I can start to solve that for beta by squaring both sides. So if I square both sides, then I get gamma squared is equal to 1 over 1 minus beta squared. Now, if I multiply through by 1 minus beta squared and divide through by gamma squared, I get 1 minus beta squared is equal to 1 over gamma squared. Now, if I take and add beta squared to both sides and subtract 1 over gamma squared from both sides, I'll get 1 minus 1 over gamma squared is equal to beta squared. Now, if I get a common denominator between these two fractions, this will become gamma squared over gamma squared. So gamma squared minus 1 over gamma squared. And then I take the square root, I would get beta is equal to the square root of gamma squared minus 1 over the square root of gamma squared, which I think you can see is clearly beta is equal to the square root of gamma squared minus 1 over gamma. So that's the general expression that we can use over and over again. So when I want gamma equal to 2, that means beta is going to be equal to the square root of 2 squared minus 1 over 2, which I think you can see is the square root of 3 over 2, which in forms of decimal is approximately 0.86603. When gamma is equal to 3, then beta will equal square root of 3 squared minus 1 over 3. In that case, that's 9 minus 1, which is 8. Square root of 8 is 2 roots of 2 over, and of course, 3. Now, this one as a percentage or as a decimal is 0.94281. I'm trying to basically do them in 5 decimal places, but showing a clear demarcation after the first 3 just to keep it from getting ugly and hard to keep up with. Now, when I try to do gamma equal to 4, then beta is going to be square root of 4 squared minus 1. Of course, 4 squared is 16, and 16 minus 1 is 15, and 15 doesn't have any square factors, so I'm going to have to call that square root of 15 over 4, and this is approximately equal to 0.96825. And for gamma equal to 5, you get beta is equal to the square root of 5 squared minus 1 over 5, which equals obviously the square root of 24, which is 4 times 6, and the square root of 4 is 2, so this would be 2 times the square root of 6 over 5. And this result is approximately 0.97980. So to 5 decimal places, that's a pretty good approximation for giving you gamma factors of 2, 3, 4, and 5. Now for gamma equals 10, which I'm really going to call 10 to the 1 because I'm going to see something kind of helpful that comes from that, I get beta is equal to, and we don't really need to worry too much about trying to find a pretty symbol because it's just going to be ugly. It's going to be a series of 3 times the square root of 11 or 1,111 or some weird stuff like that. So in this case, I'm just going to go ahead and write it as, obviously 10 squared would be 100. 100 minus 1 would be 99. That'd be a square root of 99 over 10, which is approximately equal to 0.99499. 499. Well, I could also, though it's not consistent with the 5 decimal places I've been doing, I could just shorten this for reasons that'll become clear later to 0.995. And that's pretty good. That'll get us a gamma factor of 10. So if you want time dilation to be affected by a factor of 10, then you should look for something traveling at 99.5% of the speed of light. Similarly, if you want it to be 100, which is 10 squared, then you'd say beta is equal to, now 10 squared, that's 100. And then when you square 100, that's 10,000. So this would be 9,999 over, square root of that, by the way, over 100. Again, that's not necessarily very fruitful as a rational expression, even though it's irrational with the square root in it. So I'm just going to write it out as a decimal. And as a decimal, we get 0.999 followed by a 95. And when I do 10 to the third, you might start to see the pattern I'm referring to. This is approximately equal to 0.9999999 followed by a 5. And then the next one, gamma equals 10 to the 4th. Beta is approximately equal to 0.999999995. Gamma equals 10 to the 5th gives me beta is equal to 0.999999995. 9, 9, 5. And finally, the last one I want to do is 10 to the 6th. And then I'll point out the pattern, 0.999, 999, 999, 999, and a 5 on the end. So we've now, after writing all this without you watching on the camera, I've basically stated what I've got. But as you see, 10 to the 3rd power for a gamma gave us a beta with 6 nines followed by a 5. Gamma to, or 10 to the 4th as gamma gave us 1, 2, 3, 4, 5, 6, 7, 8 nines followed by a 5. 10 to the 5th gave us 10 gammas followed, or 10 nines followed by a 5, and gamma equals 10 to the 6th gave us 12 nines followed by a 5. So evidently the pattern is for gamma equal to 10 to the n power, then beta should be equal to 0, a decimal point, and then a series of nines, and the number of nines occurring should be 2n nines followed by a 5. So that's a quick and dirty way to get your beta for a given power of 10. You just put a 0 and a decimal point down, you multiply the n by 2, and that's the number of nines you should write down. Obviously write them in pods of 3, that would be helpful, and then put a 5 on the end, and sure enough you will have the velocity required, or the beta required, to make that gamma factor. I hope you find this helpful and useful. Good day.